my advisor is Dr. Aminian. First, I would like to thank Dr. Aminian for his help and guidance for the work in this research, because without him I will not be able to get this work done. And second, I would like to thank my committee for accepting to work with me, first Professor San and Dr. Baliadi, and I would like to thank the audience for attending my presentation. I will start my presentation with introduction, and then I will talk briefly about literature review, workflow, methodology, and I will discuss the result, and finally I will summarize the conclusions and recommendation. Introduction. Since Marcellus Shale is one of the unconventional resources, so the unconventional resources is defined by the hydrocarbon reserves, which are trapped within low permeability formations such as shale rock, sandstone, and coal seam. The importance of studying the unconventional resources, you can see it from this chart, because only 31% of all the entire hydrocarbon resources is conventional resources, whereas the rest is non-conventional. Besides that, most of the producers have focused on developing gas condensate reservoir due to the drop in the dry gas prices. So they are trying to find new techniques and trying to increase the knowledge in this kind of reservoirs. Gas condensate reservoir flow is different than the conventional reservoirs, because the gas condensate reservoir flow is imbibition process, whereas the oil reservoir is decreasing saturation. That means the oil saturation in this kind of reservoir will increase instead of decrease. For this reason, the good knowledge and more techniques is really important for developing this kind of reservoirs. Besides that, gas condensate reservoirs are complex due to the continuous change in the compositions and phase behavior. This complexity comes from the retrograde accumulation in the reservoir when the reservoir pressure drops below the dew point pressure. And also it was found the critical properties of gas condensate reservoir have direct impact on the condensation process. For this reason, we study the confinement effect on the critical properties to see what is the change in the gas production, condensate production, and phase behavior. Objective. The objective of this research is to investigate the impact of pore size on within Marcellus Shale on the critical properties. And then, after we studying the change in the phase behavior, we will find, or we will study the change in the gas production and condensate production to see how the reservoir will react to these changes. Now I will talk about the literature review. The first part of the literature review is confinement effects on gas behavior. Singh was the first one who studied the confinement effects, and he investigated the thermophysical properties of the known alkyne, such as the critical temperature and pressure and density. Also, Singh proposed the equation that will calculate the shift in the critical properties due to the confinement effect. So he proposed two equations to calculate the shift in the critical pressure based on the critical pressure value of the bulk and based on the critical pressure value within the confinement. And he proposed another equation for the temperature. After Singh, Divigoda investigated the change in the phase diagram and density, viscosity, and the surface tension of the hydrocarbon under the confinement effect. Divigoda extended the work of Singh, so he proposed many equations to study the shift in the critical properties based on the molecular weight. So you can see here the first two equations to calculate the shift in the critical pressure and temperature for the 2 nanometer, the second two equations for 4 nanometer, and the last two equations for 5 nanometer. And also in these two graphs you can see how Divigoda generate his relations or correlations to find this shift in the critical properties. In order to model the gas condensate reservoir, we should understand the behavior of gas condensate reservoir, because it's totally different than the conventional reservoirs. So Feng was the first one who identified 3 different regions in the gas condensate reservoir. He identified the first region around the wellbore and around the fracture. This region has 2 phase fluid. It has gas and condensate, and both of them are flowing in this region. This region is responsible for lowering the production of the gas, because the condensate will block the gas channels around the wellbore. Next to the first region is the second region. The second region has also 2 phase fluid, but the gas only is flowing here, whereas the condensate is not flowing because the saturation of the condensate is lower than the critical saturation. And the last region, it has only the gas, the original gas of the reservoir, because the reservoir pressure in this area is still lower than higher than the dew point pressure. And we will see how the change in the saturation in each region will affect the composition and the gas and condensate production. After understanding the behavior of gas condensate reservoir, we should find the methods to model the gas condensate reservoir. The best method to study the flow behavior of gas condensate reservoir with condensate accumulation around the wellbore and around the fracture is to build the field model with local grid refinement. Local grid refinement is using the small size of a grid around the horizontal well and around the fracture. The small size grid will increase the accuracy of the simulation, so the obtained result will be more accurate comparing not using the way when we are not using the local grid refinement. Besides this method for modeling, we can use the black oil model or the single well model, the radial symmetric well, or the pseudo pressure method. In this research, I'm using the first one. I'm using the full field model with the local grid refinement. Moving from the literature review, I will talk about the workflow. The workflow of this project, of this research, starts with the data acquisition. I use this data in order to build the fluid models, 4 fluid models, and later I did the history matching for the fluid models, and then I calculate the critical properties change due to the confinement, and then we construct the reservoir models, and we run the reservoir models in order to obtain the results. Methodology. In the methodology, I will talk about each part of the workflow in details. The data acquisition starts by obtaining the data. We study the data and review in order to find which composition we should use. If you can see in this table, first the provided data include the critical property, the composition of the gas, critical properties of the gas, constant composition expansion, and constant volume depletion information. This table shows the composition of the gas that I used to build the fluid model, and the critical properties, and the molecular weight. These two figures show the obtained data from for this research. The first graph shows the pressure and volume relations, and the second one shows the retrograde liquid volume as we deplete the pressure. These two graphs were obtained based on constant composition expansion calculation. These 4 tables show the other data. What I talk about, it was the fluid data that I used, and these tables show the reservoir data that I used to construct the reservoir model. The first table shows reservoir parameters, the second one shows hydraulic fracture properties, and the third one rock properties, and the last one well production controls, or the constraint. I want to mention something about the constraint because they are really important to show the result of this research. The first constraint that I use is the bottom hole pressure, and I use 1500 psi for 30 years of production. And the second one is the gas flow rate. I use 4 million cubic feet of the gas in the first 4 months, 3 million in the second 4 months, and 2 million to the rest of the time of the project. And you will see what is the impact of each one, because each case will show how the production will, if it's sustained or it will go down. Building the fluid model. In order to build the basic fluid model, I use the WinProp program, which is like a program within the CMG package. In this model, I use the constant composition expansion calculation in order to perform the DDT behavior. The constant composition expansion will provide the data regarding the relative volume, the produced oil, dew point, and compressibility of the gas. Before going ahead and using this model to construct the reservoir model, we use the regression calculations in order to perform the history matching, to do the history matching. Regression calculation used to tune the equation of a state parameter in order to make the model provide realistic data that match the provided history data. These two tables show, the first table shows the provided experimental measurements of the constant composition expansion. So for each value of the pressure, we have different volume of the liquid, and we have different relative volume. The 3800 is the reservoir pressure, and the dew point pressure for this case was 2375. And the second table represents the result that I get from the model after performing the history matching. So you see here the result The obtained result from the model after history matching, they are close enough to the experimental data, just to make sure the obtained result will be realistic and we can use it in the reservoir construction. These two figures show the result that I obtained from the fluid model after the history matching. The first one show the pressure and volume relation. The second one show the retrograde volume. If we take a close look, we can see the green squares show the experimental data, and the dashed lines show the result of the model before the history matching, whereas the solid lines show the result of the model after the history matching. The second table show, the second figure show the volume of the produced liquid after by using the constant volume, the constant composition expansion, and similar to the first figure, the green squares represent the experimental data, and the dashed line represents the result of the model before the history matching, and finally the solid line represents the result of the model after the history matching. After we built the fluid models, I did the calculation on the critical properties for 3 different cases. We have already the unconfined case, and we have 3 different cases for the 4 different sizes. We have for 2 nanometer, we have for 4 nano, and we have for 5 nano. First, in the beginning, I used same equations to calculate the shift in the critical pressure and the critical temperature. After I found the shift in each value, I calculate the new critical pressure and temperature values based on each case of confinement. So these 3 cases will be used to construct another 3 reservoir fluid models, because we have the unconfined case, and this other 3, they represent the confinement case with different pore sizes. So after this process, we will end up with 4 fluid models that I will use to construct. I will import them in the reservoir models. Also, the obtained result from the fluid models, they are shown in this graph. This graph represents the DVT diagram. The green curve show the unconfined case, and the black one show the 2 nanometer confined case. And in this case, we can see the 2 nanometer increase the dew point pressure, and later on you will see the effect of increasing the dew point pressure on production of the gas and condensate. The 2 other cases, the 4 nano, which is the red curve, and the 5 nano, the blue curve, they are increasing the dew point pressure, and we will see the impact on the impact of the production because of this increase. The last part in the methodology was to construct the fluid models. After we construct the reservoir models, after we construct the fluid models, we will import them to construct the reservoir models. I use the CMG GIM software to construct the 4 reservoir models. The reservoir models is 2,000 feet in width and 4,000 feet in length, and it has 4 layers, each layer of 15 feet. And I place the horizontal well in the 3rd layer of the reservoir. This horizontal well has 14 fracture stages, and I used fine grid size around the well bore because it's really important to study the changes in the composition and the critical properties, the phase behavior around the well bore. The second figure shows the 14 fracture stage that I have in my model. After building the base model, I import the 4 fluid models to end up with 4 reservoir models. Each one will study the case of the confinement. The first case of the unconfined case, and the last 3 cases of the confinement with 3 different pore sizes. Moving to the result and the discussion, in this part I will discuss the result. The first obtained result was the confinement effect on gas phase behavior. We should mention the effect on gas phase behavior because it's very important to see what will happen to the production of the gas and condensate. So this result were obtained by using constant volume depletion calculations. We are lowering the pressure to see what is the amount of produced liquid and produced gas, and that will reflect the behavior of the gas condensate within the reservoir. The first case is the unconfined case, and if we take a close look, we will see the condensate will start to generate at a pressure value of 2293 psi. And the highest value of the produced liquid was around 1.7. This produced liquid represents the accumulation of the condensate within the reservoir. So that means in the reservoir, in this case, if we reach to the 2290 free pressure, the condensate will start to accumulate in the reservoir.